Welcome to the deep dive. Right now, you probably feel like you're just sitting completely still, but you're actually the center of this totally chaotic tug of war.
Yeah, exactly. On both a microscopic and, well, a cosmic level, really.
Right. So today we're looking at some foundational notes covering the fundamental forces governing the universe. And our mission is to, strip away the jargon and figure out how these invisible pushes and pulls dictate every single movement you make.
Because, I mean, it's easy to just say a force is a push or a pull, right? But the sources highlight a really critical nuance. Force is a vector.
Okay, so break that down for us. What does that specifically mean?
Yeah, so it specifically means it is a quantity with both size and direction. It's not just some vague aura of energy. It has a very specific target and trajectory.
Got it. And to keep the math universal, we measure these pushes and pulls in newtons, right?
Yes, exactly. Measured in newtons.
Okay, so if every force has a specific trajectory, how does it actually, bridge the gap to its target?
Well, that's where we get into contact versus non-contact forces. I mean, an applied force makes intuitive sense.
Like pushing a grocery trolley or pulling a suitcase.
Exactly. That's a contact force. The atoms in your hand are physically interacting with the handle, but non-contact forces, like gravity or magnetism, they act across what looks like totally empty space.
Which implies space isn't actually empty.
Right. They operate through fields. A field is essentially a region where space itself is altered, allowing forces to be transmitted without physical touch.
Oh, like when static electricity makes your hair stand up?
Yeah, or when magnets violently snap together. You're seeing electrostatic and magnetic fields bridging that gap.
And gravitational fields are obviously the most relentless of them all. Which brings up a concept from the notes that trips up almost everyone.
Conflating mass and weight.
Yes. Do you, meaning the listener, actually know the difference?
Most people don't, honestly,
Yeah.
but they're entirely different phenomena. Mass is literally the amount of matter you are made of.
And that's measured in kilograms, right?
Yeah. Yes, in kilograms. And it's a universal constant. Your mass is identical whether you're, sitting in your living room or drifting in deep space.
But weight is different.
Very. Weight is the actual gravitational force pulling on that mass. Because it is a force, weight is measured in newtons, and it constantly fluctuates depending on the local gravitational field.
Okay, the sources give us the mathematical reality check here. It says weight equals mass times gravitational field strength.
That's the formula, yeah. And here on Earth, that field strength is about 9.8 newtons per kilogram.
So wait, if you have a 5 kilogram object, you just multiply 5 by 9.8 to find its weight in newtons.
You got it. But take that exact same 5 kilogram object to the moon, and the mass is undeniably still 5 kilograms.
But the weight plummets because the moon's gravitational field is so much weaker.
Exactly. The pull weakens, but the matter remains the same.
Okay, so here's something I always wonder about that relentless downward pull. If gravity is constantly dragging us toward the Earth's core, why aren't we plummeting through the floor right now?
That's because of the normal reaction force.
Normal reaction force.
Yeah, it's a support force exerted by a surface, and it acts perpendicular to that surface. So at a microscopic level, the electrons in your shoes are actually repelling the electrons in the floor.
Oh, wow.
Yeah, that electromagnetic repulsion pushes back against gravity and holds you up like a table holding up a heavy book.
Though I see a warning in the sources about this. People assume this normal force is just the exact opposite of weight. But if I'm standing on a steep ramp, that perpendicular push from the surface is pushing at an angle, not straight up against gravity.
A very common trap. But yeah, you navigated it perfectly. The normal force shifts based on the angle of the surface, so it isn't always equal to your weight.
Okay, so the normal force keeps me from sinking. But walking requires forward momentum. I need something to push off against, which brings us to friction.
Right, so friction acts parallel to a surface to oppose motion or attempted motion, because on a microscopic scale, no surface is perfectly smooth.
So the tiny jagged edges of my shoe are interlocking with the jagged edges of the ground.
Exactly. When your foot tries to slide backward, friction pushes forward to oppose that slide. And that opposition is what actually propels you.
It's highly counterintuitive, but friction lets us move forward. Then there's tension, which operates entirely differently.
Right. Tension is a pulling force carried through a rope, string, cable, or chain.
But try pushing a rope and nothing happens.
Exactly. That's the golden rule. Tension cannot push. It only transmits force when pulled tight.
Makes sense. And we also have to account for moving through a fluid, like air.
Yes, air resistance, or drag, is another force opposing motion. It's a force from the air that fights your movement through it.
Like a parachute. You jump out of a plane, it opens, and catches a massive amount of air molecules to actively oppose your fall.
Exactly. And the faster you fall, the more molecules you hit, which creates more drag.
Right, so let's quickly recap all these notes. First, mass and weight are definitively distinct. Mass is in kilograms, weight is a force measured in newtons.
Yep. And the normal reaction force isn't just an automatic copy of your weight.
And tension only pulls. Plus, both friction and air resistance are fundamentally designed to oppose your motion.
So consider this as a final thought. You've adapted entirely to this specific gravitational field and these frictional forces.
Right.
Imagine trying to walk around a space station in 0 Newton weightlessness. Your mass is the same, but without weight locking you to a surface to create friction. You'd have to completely relearn how to use applied forces just to avoid bouncing endlessly off the walls.
That is wild to think about. That a totally different way of moving.